You're joining. You're joining.
The network disconnected.
Uh-huh.
All right. I think that. Yeah.
Again.
Yeah. Were you on this in the morning? I left audio, so you should be the only one.
Yeah, but someone has to try whether this works. Someone should try to. I can't.
You cannot?
No, I mean I cannot. It's. I'm not gonna hear myself, right, from my laptop. So someone else has to speak. No.
So from Zoom, you can say test speaker and
Where?
and then say hello 111, and then it repeats it in the whatever speaker is available.
It's probably easier. So.
Audio.
Yeah, but it's easier if someone says something. The speaker mic. Yeah, but it's this one.
So change it. Change it.
Yeah. There you go. Yeah, yeah. Like that?
So ask somebody on
Yeah.
to say hello, whatever.
Yeah. Yeah, Amar, can you say hello?
Yeah, can you hear me?
Yeah, very nice.
Yeah,
Okay.
sorry I can't come in person, but I'm enjoying the lectures very much. Thank you so much. This is wonderful.
It's a pleasure to have you. Thank you for being here. Hopefully you can, I mean, I know I'm on the side, but hopefully you can still see me.
I can
Move
see,
around.
as I said, it's one yesterday was wonderful. Thank you so much.
I'm glad you like that. Good. Hopefully today is going to be similarly interesting. All right. So let's get started on this afternoon's material. I plan to talk a bit about the structure of algebras and coalgebras, the sort of stuff that underlies these spiders. These spiders are interesting algebraic objects on their own. So I'm going to start from there, and then, as usual, you have questions, you want to go deeper into one of the topics, we'll do so. But I'll start by giving you a few results and sort of a bit of backing, and we take it from there. So just to sort of recall what we discussed, we can define these spiders, I guess, these special boxes. Yeah.
Sorry to interrupt. I'm not seeing your.
Yeah. You're right. You're correct. Thank you so much. I just, while you were saying it, I realized that I wasn't sharing my screen. Thank you for reminding me. Fantastic. That should be fine now. Thank you. As I was saying, there's these spiders, which you can define, these boxes that have arbitrary number of inputs, arbitrary number of outputs, and carry some decoration, which is known as a phase, at least in the context of quantum. And now these are really just a way of having to keep track of too many equations. So we write spiders like this, but really they are not these are variadic algebraic objects. They're algebraic objects with arbitrarities, so they're families of objects, if you will. And we can focus on some generators, so like a set of simpler objects that when composed give us all of the possible combinations. So we observe that if you want to make any number of legs, all you have to do really is start by applying a bunch of these multiplications, as I shall call them, which have 2 legs in and 1 leg out. You apply n-1 of those. Then in the middle, you apply a single rotation, and then you apply these co-multiplications. Again, 1 leg in, 2 legs out this time. And the point is that the particular choice of connectivity doesn't matter, as in whatever the fusion rule says, which is this sort of spider theorem that says I can take 2 spiders with any number of inputs and outputs legs connected by at least 1 leg. So I should have been a bit more precise today. You can have many legs that connect them. And as long as there is at least 1, they all sort of disappear. So this afternoon, I will do it properly. Say N1, N2 input legs, M1, M2 output legs, and let's say K legs shared, subject to the requirement that K is greater than or equal to 1. So there is at least 1 shared leg. It doesn't matter how many input legs there are, how many output legs there are, those will be preserved in a sense. The middle legs will be cut. Well, actually, they will just fuse into the big blob of things. So I'm going to end up with a single spider. The 2 phases will add up in some sense, which we'll discuss more later on. And we're going to have N1 plus N2 legs on the left. And we're going to have M1 plus M2 legs on the right. Something like that. Now, this kind of rule, as it is stated in most presentations of the ZX calculus and these other graphical calculi, is actually a derived rule, because algebraically, this is a family, it's a meta rule, it's a family of rules parameterized by the number of inputs and outputs. And if you state it as a family of rules and you're doing some algebra, you probably have to then check that the rules for various numbers are consistent with each other. And this is not entirely obvious. So from an algebraic point of view, it's easier to study an object defined by simpler pieces, like a finite set of pieces, a finite set of rules, and then derive these bigger, more useful rules as a consequence. And this is known as the fusion rule today. But in the early days of categorical quantum mechanics, this was known as the fusion theorem. So it was the result that you had to prove. Now it is so common that it's stated as a meta rule, but at the start, it was actually a consequence of something simpler. So what is the algebraic structure that we care about? There is a monoid, and this is a monoid in the categorical sense of the word. So it's not a monoid in the sense that there is a set being acted upon. There is a set in a sense, but it's not all there is. It's a monoid in the sense that it captures the abstract rules of a monoid just diagrammatically. So there are some equations of diagrams that capture the essence of the rules of a monoid. So they're going to capture unitality and associativity. So this is going to have two rules that say that the unit, so this is called the multiplication, and this is called the unit, like those of a monoid. 2 rules that say that the unit is a bilateral unit in the usual sense for a monoid, as in you apply it on the left leg or on the right leg and it gives you the identity. And then there are 2 more rules that say, in fact, 1 is enough, that say that this is an associative operation. So if I apply it with this basic tree, or I apply it with going on the right first, then I get the same result. And now this makes it a monoid. This is what a monoid is in the abstract sense. A monoid is from a set theoretic sense, it's an operation which is a binary operation. It is unital, left and right, and associative. That's it. Then if you want commutativity, you can also add commutativity. And commutativity is just a statement that if I take the 2 inputs, or if I first swap and then apply the monoid, I get the same result. However, and this is something that's kind of important, this requires symmetry. So it requires the existence of one of these braids or symmetry isomorphisms. Not every category has one. Not every setting where you see monoids has a natural notion of swapping inputs. Well, almost all of the practical ones do, but sometimes these swaps are not self-inverse, like in the case of braidings in 3 dimensions. And then you have to be a bit careful how you phrase this particular property, because it's not like there you have 2 different directions that you can braid, and there's different gradations effectively of commutativity that you can have. But for now, we'll keep things simple. We think of Hilbert spaces as our main setting, and this is unequivocal in the case of Hilbert spaces. And now you can take the same operation and dualize it. You can flip everything left to right, and you get a different set of equations. You get a different operation, which is called a co-multiplication or a copy. So I'm going to go with a technical term. This is a co-multiplication, but people also say it's a copy. And there is a co-unit. Everything is just co. Co just means flipped left to right. Co-unit or a delete. And the branch of algebra that studies structures that look like algebraic structures but go the other way is called coalgebra. Kind of unsurprising. So, and it's a big field of study in its own. And you can take the same exact equations and you say you have a co-unit law that says that if you delete one branch of a copy, it's as if you did nothing. If you delete the other branch of the copy, it's also as if you did nothing. And then there is a co-associativity law that says that if you copy twice and the second copy is on the left or on the right branch, it doesn't matter because you're going to end up with 3 identical things, right? And soon I will surprise you by saying that not everything looks like a copy, but they're all coalgebras. And you have a commutativity. You can just call it commutativity, honestly, because co-commutativity is a bit hard to say. It's a bit hard on the tongue, which says that if you do one of these copies or co-multiplications and you invert the order of the arguments, then you get the same result. And why I call it copy and why I call it co-multiplication will soon become clear, because I'm going to give you 2 examples. In fact, it's going to be the same structure. It will look like a copy from one perspective and like a co-multiplication from a different perspective, but it's going to be the same map. So really, there's these 2 different perspectives that you can take. But for now, these 2, I've chosen similar notations, but they don't really interact yet. So let's say that I have a monoid. This is a monoid. And I have a comonoid. And they're on the same system. I have deliberately not included the system underneath because it's the same. It's the same for all wires. So it's x, 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 like that. Same for all wires. So I can compose them and I can ask, what is this? That's one way to compose them. That involves pieces from the 2 structures. We don't know how they interact. We know nothing yet. All we know is that you do a multiplication and then you do some co-multiplication. But what does that mean? Is it the same if I instead do first a multiplication, first a co-multiplication on the left and then I multiply on the right, like that? What about doing it the other way? What about doing something like this? They all have 2 legs in, 2 legs out. They're all connected. So if you've seen spiders this morning, the answer is you expect them to be exactly the same. But here we're just doing some abstract algebra. We don't yet know. The way we know that they're the same is we impose equations and we say that a pair of monoid and comonoid that satisfy these equations is called the Frobenius algebra. And these are known as the Frobenius laws. And now if, and that's a big if, my notation didn't deceive me, and I pick the co-unit and the co-multiplication to be the adjoints in some sense, in the sense of the category that I'm working in, of the multiplication and unit. So I say my co-multiplication is really defined to be just my multiplication, but adjoint. And my co-unit is defined to be my unit, but adjoint. So they are related. I really only define, I have a bigger setting where I can take adjoints of my maps. Adjoints invert inputs and outputs and take adjoints like in unitary matrices. Now I only have two pieces of data that I have to give. I only have to give this data here, and everything else is sort of derived from it. I specify multiplication and a unit, and the other two follow because I just take the adjoints. If I have a structure like this, it's not just a Frobenius algebra, it's called a Dagger Frobenius algebra, from the fact that it's derived from two pieces by taking adjoints. And these are special. They have some interesting properties. And now if these pieces are obtained by adjoints, I might ask one more question. I might say, okay, look, what about this? This is gonna be a state. What about the copy? A copy followed by a co-copy, what does it do? Can I cancel them out? Can I not cancel them out? Do they mean something? Again, if you see spiders, you know that these should just give the identity. What I expect to see is that this fuse into a single dot with no angle, and then I can remove it and I get the identity. And indeed, you impose this as an equation, and you say that if your algebra satisfies this property, this equation, it's called a special. It's called the special equation, speciality or specialty. So Frobenius algebra that satisfies this is a special Dagger Frobenius algebra. As in, it means that this map is an isometry. Okay, it's inverted by its own adjoint. So that's what an isometry is. An isometry is a map such that, so V is an isometry if and only if V dagger V is the identity. Right, so that's the definition of an isometry, and this just means the copy is an isometry. And now the reason I introduced all of these various pieces is that I am now in a position to prove that if I write any, so this was one of the spider theorem. If I have any combination, any graph that involves multiplications, units, co-multiplications, co-units in any form, let me just do it in a bit more, in a more interesting way, like that. Like that. Any connected graph that is composed only of these pieces, then you don't really need to know anything about this graph other than the fact that it has n inputs, m outputs, and then you can prove that it just collapses onto a single spider as defined before. So this was the kind of result that people looked at. You don't even need commutativity for this. You only need commutativity if you start introducing swaps around. If you introduce swaps around, then you have to be careful. But without swaps, if it's just a plain graph, a planar graph, I should say, so it's a connected planar or planar graph consisting only of those pieces, then the spider theorem tells you that you can fuse all of them together. Why? Well, because whenever you encounter a piece that looks like this, you can use associativity to just swap it into some normal form. Whenever you encounter a piece that looks like this, you can just fuse it together with the unit law. So you can remove the little dangling thing. Whenever you encounter a weird piece that looks like you can't do much with, like this one, that's in the form of the Frobenius law. And so you can change it into something like this and then continue simplifying. And so really all you do is apply these rules until you bring the spider to the normal form that defines this. Because remember that this was defined to be just a normal form for that particular graph. So it's something like this. Yeah, that's just its definition. Okay, so really these structures are they're one layer of abstraction over something a bit simpler. And now, why are these interesting? Well, there's a result that says that if you have, and this was one of the key insights of the categorical quantum mechanics program, that if this is a special commutative Dagger-Frobenius algebra, so if it satisfies all of those axioms that I presented before in finite dimensional Hilbert spaces, this is true if and only if it is in the form of a basis. It's an observable for any basis. So there is a unique orthonormal basis such that the copy is the copy for that basis. And delete, let's say, is the delete for that basis. That's it. So these things are observables. They are, well, technically they're not observables. They are orthonormal bases, which is not quite the same as an observable. And that's a point worth making. And it's a point that I will make now. But they are a different way of characterizing orthonormal bases. And now if you drop commutative Dagger-Frobenius algebra, or if you consider the fact that these might not be commutative, you might wonder what is an example of a non-commutative one. You can easily make a non-commutative one. There's a standard non-commutative one that you can make, which is called the pair of pants, or the pair of copants, if you want. So you take the cap and a couple of wires, and you make them in the shape of a multiplication. And then you take a bend, and you make it in the shape of a unit. And then it turns out that this is also a Dagger-Frobenius algebra. It's not yet special because we'll need to normalize something, but it is almost special. And we can check, indeed, if we apply our multiplication to our cup, we can just straighten the wire and we get something like this. And that's the same as applying the multiplication to the cup on the other side. So this definitely works. Okay. What about associativity? Well, if I first do a multiplication on this side, and then I do a second multiplication like that, then I can sort of pull the two cups down so that it looks like it's symmetric left to up to down. And it will look something like this. And then I pull them the other way and it becomes something like this. So it's also associative. That's good. Therefore, if I take the adjoints, I'm going to get co-unital and co-associative. That's fine. It is not commutative. So if I try to draw a swap here, and then a multiplication, I just have to follow the wires to figure out whether it's commutative or not. So I check, where does one go? Well, I follow. One is here. I check, where does 2 go? I follow it all the way, it goes here. And then I check that 3 goes here. Now, if I take the other, and I do the same game. So let's start with 1. 1 goes here. 2 goes here. And 3 goes here. So they are not the same. So this is an example of one of these structures that's not going to be commutative. And we have to sort of generalize our result a little. But is it a Frobenius? I mean, this is just it's a monoid. It's a comonoid. Is it Frobenius? Does it satisfy the Frobenius law? Again, we just have to plug things in. So first you copy, and then you multiply. that. And you can indeed check just by pulling the wires one direction and the other that you get the same as doing first a multiplication, then a co-multiplication. And it's the same as doing a multiplication on the other side first, like that. And like that. So that's fine. That is Frobenius for sure. The last thing we need to check is that this is truly a special one, and it's not yet, because this is not the identity. It's the identity times whatever this loop is. And this loop of wire, which I'm going to put some arrows to show that this is not a dot, it's an actual loop, empty loop. This is just the dimension of your system. So if this Hilbert space has dimension D, then the loop of wire is D, because it's the trace of the identity, just to be clear. And so this is the identity times this scalar D. And it's not really symmetric. So sorry, it's not special, but I can make it special by just dividing one of the two pieces by 1 over root D, and that works. So I can, for example, take 1 over root D here, 1 over, and I can do root D here. There you go. So the unit law is preserved. The multiplication and co-multiplication still associative because there is the same number of arches left and right. The only thing that has a different number of arches is the special law, but here I get a factor of 1 over D, which cancels out my D at the end. So that works out. So this is special again, but it's not commutative. So the question is there a slightly more general result for these kind of algebras where I have speciality, I have associativity, co-associativity, Frobenius. So I have what is known as a special Dagger Frobenius algebra. And an important result that generalizes this orthonormal basis result from before is that these in finite dimensional Hilbert spaces are exactly finite dimensional sister algebras. That's the important part. And it sounds a bit weird that they are finite dimensional sister algebras because we are used to thinking that sister algebras are embedded as algebras of matrices. But actually, all you have to do, an algebra is any operation on any vector space. And if you don't know what a sister algebra is, it doesn't matter. I'm going to tell you in a second that it's just an observable. But for now, you take this multiplication and you ask, how do I see this multiplication as a multiplication of matrices? Well, all you have to do is embed it into the matrix algebra. So you just ask, what is the matrix algebra? Well, the matrix algebra is the pair of pens, because this is how matrix composition works. If you take a matrix M and a matrix N, actually, let me do it properly. You take a matrix, the linear map, and another matrix, and you think, okay, composing these matrices is putting one after the other. But you don't have to put them one after the other. It's actually enough to put the inputs on one side and treat them as if they were states, like state matrix, vector matrix isomorphism. And then you apply the pair of pens to them. And then you pull all of the wires, or if you want, you follow the line. It sort of starts, this is the input, so it goes all the way down, comes into N, comes out of N, comes into M, and goes out. So this is the same as the state that represent their composition. So this is the algebra that represents composition of matrices. So this is the matrix algebra. And we can prove that all of these are sister algebras just by taking the multiplication for any one of these structures and embedding it into the matrix algebra. How do you do that? Well, really, you take this map. That sense, it goes from your Hilbert space to the algebra of matrices over the Hilbert space. And this is what H star H. And it turns out it's a algebromorphism. It maps your multiplication onto the multiplication of matrices, your unit onto the unit of matrices, and so on. So you don't really have to, you can see them as algebras in the normal sense, or as matrices, matrix algebras, and everything works out. So this result effectively proved that if you want to think about quantum observables, you don't have to think of them in terms of basis. You can think of them in terms of spiders or structures. So really spiders are just an incarnation of a choice of basis. And two of them are enough, but you can make spiders out of any basis you want. So if you take the Z spiders, so these typically correspond to the Z basis. And we define the ones for the X basis because it's enough to have rotations in Z and X to do anything. So we have two kinds of spiders, but we could in principle define spiders for any basis we want. It doesn't have to be just Z and X. Yes?
This morning you said there was a problem with the Y. What was the problem? Why did you say that?
Yeah, I think, yeah, this morning or yesterday. I don't, yeah, yesterday maybe. Let me show you. So the idea is if you now have a matrix, some basis change matrix that say goes from the Z basis, transforms the Z basis to the Y basis, okay? What is an example of such a matrix? Well, if you are in the Z basis, in the block sphere, and you want to go to the Y basis, you just do this. You just rotate by X, about X by minus pi over 2. So I could, for example, take minus pi over 2. And its inverse is from the Y basis to the Z basis is the rotation by pi over 2. So if I want to make, I can make spiders for the Y basis. I can define my Y spiders by saying that they are, I want to start with Y legs. Okay, so these legs are in the Y basis. I'm just putting some color to make it clear. And I first have to go from Y to Z. So I have to do whatever it is that I have to do to move from Y to Z. That would be Y to Z is a pi over 2 rotation. And I apply 1 to each leg. So each leg goes from the Y basis to the Z basis. And then I do my Z spider. So I do the operation in the Z basis, and then I go back to the Y basis. Come on. So here's Y again, and this is Z again, something like that. So now I can define these, and these will define a special commutative Dagger-Frobenius algebra for the Y basis, and that's fine. That is, there is one for each basis. This is the one for the Y basis. That's okay. That works out. It also happens that because you've taken a orthonormal basis as your starting point and you apply a unitary matrix to it, then you get an orthonormal basis as the endpoint. So if the first spider was commutative, then the second spider is also commutative. You don't have to know this. It's not a fact of Hilbert spaces. You can prove it diagrammatically. All you have to do is look at for example, the equations for commutativity. You say, I want to prove that my Y spiders are commutative. How do I do it? Well, I start and I put a swap. Then I expand it into its definition. And I say, okay, it's pi over 2. Then it's a Z spider. Then it's minus pi over 2, minus pi over 2. And then it's the swap. Then I push my change of basis matrices, which are local to the individual legs. I push them forward through the swap. So I get pi over 2, this, minus pi over 2, minus pi over 2, like that. And now I use the fact that the Z spider is commutative to obtain my original Y spider. So pi over 2, minus pi over 2, minus pi over 2, like that. So I don't really have to know that these are related to orthonormal basis. I can prove that one defines the other just by manipulating the diagrams that compose them. However, here's the issue. In the case of qubits, it is a fact, it is a convenient fact that I did this morning. Actually, let me start with, it is always true that the empty spiders give you the identity. This is not true just for X and Z, it's true for all of them. Any zero, whatever the basis is, if you do a 0 angle rotation, it's a 0 angle rotation. There's not much to do. So even if I take a Y spider with no angle, that's also the identity. Whatever, if I take a spider on the basis of the Hadamard, it's also the identity. It doesn't really matter. However, it is a convenient fact for qubits that the cups and caps for the two, that the cups and caps for the two colors are the same. This is true only for the spaces in the form Z2 to the algebras over Z2 to the n. So when your group is just a product of bits under XOR, so qubits are one example, but effectively qubits and tensor products of qubits are the only examples that you get. This is very convenient because you can say that the cup and the cap are defined to be, they have no other definition technically, they're defined to be the cup and cap for one of these bases. And typically we pick the Z basis because I don't know why. Okay, it's a computational basis. It's kind of good to know that you're transposing in the basis that you typically use to write your matrices. So that matrix transposition and these sort of transposition of legs are the same operation, which is convenient. In the case of general systems, you don't get that, but it's also true that you don't get that the leg for the Y spider, the cup and cap for the Y spider are equal to the ones for the Z spider. So this is not true. In fact, you can easily check what these cups and caps are, and I will. Okay, proof. Open the definition of the cup. It's defined to be the one for the X spider, sorry, for the Z spider, followed by minus pi over 2, minus pi over 2 to go back to the Y basis, right? So it's you do the cup in the Z basis and then you rotate back. And now what I can do is I can be a bit clever and I can say the cup for the Z and the cup for the X spider are the same. So I replace the one for the Z with the one for the X, because it's convenient more than anything, because now I have things that are all in the same color. They're all in the X basis, so I can fuse them. I fuse and I obtain something like that. I unfuse to shift it up one of the legs just to keep things simple. Unfuse. And I obtain this. And then I change again the color to bring it back to a clear situation. And I am left with this. And this is, what state is that? What does the pi spider do? What is this? From this morning? It sends, if I plug 0 into it, I get 1. And if I plug 1 into it, I get 0. So what is it? It's the NOT gate. So what I have is the same as the original Bell state, but with a NOT gate applied to one of the legs. And this is, instead of being the phi plus Bell state, sorry, the phi plus Bell state, this is going to be the psi plus Bell state, which is different from this state here. It's not the same. So the Y transposition is not the same as the Z transposition, which means that if I take my Y spiders and I try to bend a leg, I take a Y spider like this, and I try to bend the leg down. So I try to say, oh, I take this spider and then I'm bending the leg down. Really what that means, we might be tempted to think, oh, bending the leg just means you bring it to the input. But that's true for Z and X. It's not true in general, because secretly it's just a convenient notation for saying you apply the cap, whatever cap was, and the cap is the one in the Z basis. And we just seen that the cap in the Y basis is not this, right? So we introduce two knots just to get the cap in the Y basis. So we do something slightly more clever. We keep this cap, and then we do not like that. And then we say, oh, look at this. This one, this is now the cap for the Y basis. So I repackage it a little and say, okay, it's the Y spider. There's a cap for the Y basis, and then there's a knot hanging in there. So really it's similar to the transposition, but I've gained a knot gate on one of the legs. So it's different from what we did before. That's why the Y spiders are a bit more inconvenient to use. They have this issue with the directionality of the legs. So you can't really, for example, you cannot write for a CY gate. So for a CX gate, I could have written something like this. C naught, right? Is something like that. Because I can write this one, or I can write this one, and they're the same because I can twist the legs of the two spiders up and down as much as I want. In fact, I could have also written slightly more weird. I could have written it like this, or I could have written it like this. They would have also been the same. They're all the same. For the control Y, how do you make a control Y? Well, you want to have your control, and the idea is that the control will take whatever input state you have in the Z basis, so something in the form C pi, and it will copy it to, again, the output of the control qubit, so that's fine, and it will copy it through the leg of the C naught, the shear leg between the two, and this becomes C pi. And that's okay, because the direction doesn't matter for this spider. Like this copy map is kind of irrelevant. You just follow from one leg to all the other legs. It copies in all directions. So there's nothing to be particularly careful about. Now I want to apply the negation, so the pi gate to the Y basis. So I want to have a Y spider somewhere there. But of course, in order for this to happen, I have to be able to fuse these with a pi spider in the Y basis. So I have to somehow go from this state to the corresponding Y basis state. So I have to apply an X to Y basis change, which is a pi over 2 Z rotation. So in the middle, I place a pi over 2 Z rotation. And that is the CY gate. CY gate is the control, copy the control, change the basis of the leg that goes into the part that will become the knot into its own basis, and then it fuse with it. Now, the issue is that I've written it like this, but this makes no sense. This is not a well-defined notation. It is extremely tempting to write it like this because I am imagining that dynamically the process is I put something into the copy, it gets out of the two branches of the copy, it traverses the pi over 2 gate and enters the Y spider. But there is nowhere in the diagram that says that anything is entering the spider. I did not give a directionality to the leg. And this is, I don't know what that is. So what I wanted to write was this. So you have to just be careful with the direction of the legs that come in and out of the spiders that are not X and Z. That's why people like to work with X and Z and really dislike working with all of the other ones. Even though there are a lot of applications like Pauli gadgets, so the generators for all rotations, they are naturally expressed in terms of X, Y, and Z basis. And so there is a nice sort of push to say, oh, I want to have my blue, my red, my green spiders so that I can quickly distinguish which basis it is in. And that's good, but you have to pay some attention. So it's fine. To be fair, and it's worth mentioning now, this is not a problem just for Y. If you're working with an arbitrary finite abelian group, in fact, if you're working with any arbitrary finite group, okay, so you're in the group algebra for a finite group, whatever that group is, it could be, for example, I don't know, S4. Why not pick the group of rotations of a cube? then you always get a copy and delete for the computational basis. So for the basis that's labeled by the group elements. And this is special and commutative. So we say it's a Dagger special commutative Frobenius algebra, like that. And you also get another algebra, which is, I'm just going to write in this order to explain where it comes from. That is just a rescaled version of the multiplication. So it's a group multiplication. It sends, this one is the map that sends G and H into G dot H in group, overall G's and H's. And this one is the group unit. And I have, if I want to make it special, I actually have to put a normalization factor in front, but that's fine. It's just a normalization is fairly irrelevant. And now the problem with this one is that it's going to be a Dagger special Frobenius algebra, but it is commutative if and only if G is abelian. So it is not commutative because it's a group multiplication, quite literally applied to the computational basis. So it's not necessarily going to be commutative, but sometimes it is, sometimes it isn't. Regardless of whether it is, it is never true except for Z2 that the two caps are the same. So if G is different from Z2 to the N, so bit strings under XOR, then the two caps are never the same. The two cups are never the same. And so even the C naught cannot be written in the la-di-da, I don't care about the direction version. And I have to distinguish between the control add, which is a better name for it, I believe, and the inverse of the control add. And these two are not the same map. This one sends G and H, and let me do it in a different color, sends G to G, G, H, G, what did I define it on the left? Yes, together become G dot H in the group. The other one sends G, G, and this is kind of funny. You go backwards, H comes in. What is the co-multiplication? The co-multiplication subtracts from the other leg. So if you check what the adjoint of this map looks like, you take this map, and let me do without normalization just to keep things simple. It's G, H, G dot H is the result when applied to G and H, something like that. If you take its adjoint, you can look. It gives you the co-multiplication, which is again some GH, but now you have the kets for the original inputs and the bra for the original output. But you can do some group theory hocus pocus and re-index these. You can redefine, you change the variable name and you sum it into GK and becomes G, K minus, well, K is a G, so I define what? I want G dot H is K, so I want H is G minus 1K, there you go, G minus 1 dot K. Okay, so now it looks again like it takes an input, but what it returns is the superposition of all possible pairs that sum to that input. So it sends 0 to the superposition over all the group elements that sum to 0, 1 to the superposition of all the group elements that sum to 1, and so on. So really the result here is G minus 1 dot H. And so you apply one and then the other, you get G times G minus 1 times H, which is just H. So it is really the inverse. It's just the C naught is no longer a C naught, it's now called a C add or a C mol. Whatever you want to call it, depending on whether it's abelian or non-abelian. So you get the same problem as the Y spider, that in that you have to now remember which legs are in and which legs are out, even for the X spiders. And the X spiders, even for abelian groups, it's still something that you have to remember. Luckily, it's quite easy to twist legs around. It's not particularly complicated because the basis change matrix is easy to write. It's something that this morning I didn't introduce, but the ZX calculus has multiple pieces in it. It has these Z spiders. And I guess at some point, someone will have to ask me what these phases mean. There's the X spiders. And then there's a basis change matrix, which I will define to be the matrix that turns the Z basis into the X basis. So that actually the spiders, the X spiders, are not primitive anymore. They can be defined to be the Z spiders with basis change on all legs. So H dagger, H. So this is the Hadamard or the Fourier basis matrix. Hadamard matrix seems to be sometimes ambiguous as a term. It is characterized by the property that if you apply it 4 times, or if you apply it 3 times, I guess you get its adjoint. And so we define the antipode to be the Hadamard matrix applied twice. It has the property that if you do it twice, you get the identity, and it's a very useful map if you're working with groups because it is the group inverse. So the antipode is the map that sends an element of the group into its inverse, and vice versa. So that's why it's self inverse. So you now have really 2 basic ingredients that you care about. You care about these spiders and this Hadamard matrix, plus the rules that tell you how it behaves, but actually people still define and work with X spiders because it's useful to not have to carry around too many boxes flying through your diagrams. And to add something, the phases themselves are interesting. So let's just ask, what is a rotation by alpha in the case of a qubit? How do you write a rotation by alpha in the Z basis? That's the easiest one because all of these are in their own basis. It's just the change of basis makes them look weird, but if you take the right basis, they are diagonal. This is a diagonal matrix in the Z basis. And you might, of course, up to a global phase, it doesn't matter, but one way to write it that makes it clear that there's just 1 degree of freedom is to write it like this. And say it is the matrix which has 1 on the top and e to the I alpha on the bottom, 1 on top left, e to the I alpha on the bottom right. And this, it's not perhaps the one that you see in some textbooks, but it is the one that gives you exactly the Z matrix, the Pauli Z matrix for pi. So yeah, it is not symmetric in a sense, but it has the advantage that you can clearly see that there is 1 degree of freedom. Okay, so what is the structure of these rotations? What is the structure of these phases for a qubit in general? Well, how many diagonal elements do we have in a qubit? We have, if we have d dimensions, how many basis vectors are there? In 4 dimensions, how many basis vectors do we have, for example? It wasn't hard. So because we want to fix a global phase effectively, one way to do that is to say 1 element of the diagonal in a chosen position is always 1. So we pick the first one to remain 1. And then we say e to the I alpha 1 ... e to the I alpha d minus 1. And so really what this is, the general structure of phases is it's a vector with d minus 1 components, and each component is kind of modulo 2 pi. So it's just a vector of angles. And if you want to write it compactly, you say that this is in, I don't know, r modulo 2 pi z d minus 1, if you want to be mathematical about it. But it's really just alpha 1 ... alpha d minus 1 are between 0 and 2 pi, 1 included, y excluded, it doesn't matter. They're modulo 2 pi. Mod 2 pi. So the angles, really. The phase group is very simple. There is nothing special about it. How do you see that that it is actually a group? I said it's a phase group, but how you see it's a group? Well, you can either observe that even if you're not in quantum theory, where I can give you an explicit expression for what this is, for how this works, I can still observe that, well, I certainly can compose them. So it's at the very least a monoid. Right? So it's a monoid for sure. And then there's going to be an equation that tells you that if you take one of these and apply the antipode to it, the antipode commutes through it by changing the sign, because that's the, and therefore you have inverses and blah, blah, blah. But this is kind of general and pointless right now. More interestingly, what happens if you move to infinite dimensions? Because that's the case that maybe we do care about. So what if we are in a situation where we want to work with, I don't know, L2 over R. It's kind of nasty, but in its own ways. You don't necessarily work over L2 over R. You might not want to. Let's start with an easier one, okay? Let's start with the basis of little L2 for the natural numbers. Still infinite dimensional Hilbert space, still separable, so all good, but easier to deal with. And you have the basis, a basis which is E0, E1, for all natural numbers. So there's an orthonormal basis, which I'm going to take to be the computational basis, if you will, which is EJ for all J in the natural numbers. Good. Now, what can I do with this? Can I make a spider out of this? And the answer turns out to be a bit complicated. Certainly, I can make a copy map. A copy map is still going to be an isometry. I can write this map, and I can define it to be the map, the isometry that for every J in the natural numbers sends EJ to EJ, EJ. This is an isometry. It is co-commutative. It is, that's it, roughly. And it is special because it's an isometry. It's co-commutative, and I think, oh, this is weird. Can I do this? Yes, because finite and infinite dimensional Hilbert spaces, by definition, all have an adjoint. That's part of the definition of what a Hilbert space is. So if a bounded operator exists, then it has an adjoint, which is also a bounded operator. So in that sense, we are safe, and we define it to be just the adjoint of the previous one, and it's again a finite, nicely defined bounded operator. The problem we have is that the moment we try to define a unit for this thing, we're in trouble. Because what is a unit for it? The unit would have to be, in a moral sense, at the very least, the sum over the computational basis elements. How do we know that? Well, let's start with what the counit has to do. So the counit has to take a computational basis element, EJ, and it has to remove it. It has to delete it. So it has to return 1. It has to be some vector. This has to be some vector or some bra. Let's call it some bra phi, such that if I take the inner product of this bra with a computational basis vector, I get 1 for all of the computational basis vectors. And the computational basis vectors are normalized. So this tells me exactly what the coordinates of this bra are. And so I can immediately write this, and I'm going to have to put quotes around because I don't know what the thing on the right means. Well, I do, but maybe you're not convinced that it makes sense. I'd like to write this, but that is unbounded and not normalizable. How do I know? Well, I can just take the bone, the appearance of the bone. The bone is sum over J. In fact, I'm going to skip the index because this is true for all dimensions. Sum over K, EJ, EK. So it is sum over K of 1. So it is the dimension of my space, which happens to be the cardinality of the natural numbers, which is infinite. So not very nice. Not good, not very good. So it turns out that you cannot define these spiders with units for infinite dimensions, but you can define spiders with approximate units for infinite dimensions. So you can say there is a sequence of these units that are approximate, such that in the limit for k tending to infinity, I recover the identity. And I define this to be just the sum up to k. So what people have done is define the sum from 1 to k, or from 0 to k, I guess, of the computational basis states. This is of growing norm. It has norm k for all k. It becomes larger and larger, larger and larger, actually root k, larger and larger and larger and larger and larger. It doesn't matter in the limit up to some, actually in the limit, you can prove that the expression on the left converges to the identity operator. But you cannot actually have a unit anymore. And this is the price you pay for wanting to work with bounded operators and Frobenius algebras. And so the structures that you get are weaker. They're called H-star algebras. And people work with them for a while. But there's a bigger issue, which is you cannot use cups and caps in infinite dimensions. Because if you have a cup and cap that satisfy these snake equations, then what you can do is you can ask, what is this? This is going to be the trace of some block. So it's the trace of the identity. And the trace of the identity is again infinite. So again, sad face. Yes. Yeah. So the infinite dimensional environment is really what creates the issue. So you would be able to write the operations of the von Neumann algebra diagrammatically. You wouldn't be able to do full diagrammatic reasoning because you'd lack the cups and the caps, but you would still be able to do some diagrammatic reasoning over those operations. Like if von Neumann algebra is associative, I can write down the multiplication operation, and that is a genuine box that works kind of like this, but it's not a Frobenius algebra. That's, I guess, my. Yeah, you mean the cups and caps on the actual algebra space? Why would they be okay? Because it's infinite, so they would have to be like if you compose them in a loop, you still get the trace of the identity, right? If the underlying space is still infinite. So maybe you get a traced monoidal category, you just don't get a compact closed monoidal category. That would be good. Yeah, I never really looked at that. Yeah, worth it. I'll look into it. Interesting. You can do a lot of things just with a trace. You don't need the cups and caps are nice, but yeah, nice. Still, the general characterization of what these infinite dimensional families of algebras look like is not yet done. Like people stopped at the finite dimensional ones. Were happy that they were finite dimensional sister algebras, and then sort of got a bit, tried to do the infinite dimensional ones, and then got tired when it didn't work out very well, which is fair. But the finite dimensional ones are still pretty nice because you can use them to, and we'll see it tomorrow in the morning lecture and then in the afternoon lectures. You can use them to do a lot of group representation theory. You can use them to, you can do representation theory with these X and Z spiders for arbitrary groups. Some representation theory, not obviously everything, but if you enrich them a little, you can do quite a lot of things. And they do extend to infinite dimensions as long as you're willing to cheat a little and presume that the real numbers are not really the real numbers. They're just a very fine discretization of the real numbers that kind of goes a bit beyond the real numbers and maybe wraps around. So they are, it's like a cyclic group, but one which has a lot of points and has so many points that they happen to cover every real number many times. So if you use non-standard analysis as it is called, you can actually extend all of these techniques to some abelian groups, some abelian Lie groups, even non-compact ones, locally compact ones. Some. It's not clear how you extend it to arbitrary compact Lie groups, for example. It's not. The finite dimensional non-abelian ones are kind of nice. I mean, they are not great, but they are still well behaved. The infinite dimensional ones, it's just how do you do a discretization of some of these groups is unclear. Like some of these groups don't really admit nice discretization, nice discrete subgroups that get finer and finer and finer and cover the entire group. It's a special property. Every abelian one does, but non-abelian ones don't. Not all of them do, at least. So it's unclear how you extend beyond the current status. For the basic things, I think I'll stop here. And that's a reasonable introduction to Frobenius algebras and basis and the issues that you get. But questions, I'll take any questions that you have, and we can go over more material that you'd like to cover. Also for you online, Amir? Still there? No? Gone. Okay. Well, then, are we recording this part? Okay.
So the only thing is that if somebody's asking a question and they can't hear you, maybe.
I'll repeat the question, exactly. Yeah.
Yeah, I would like, seeing from what you're saying.
Yeah.
And all these compositions, things like that, there are some assumptions again that we're not saying for the linear product. All this stuff that is, it's hidden there. I see, it works. The both things are well defined. But we discussed today, if one would like to apply some of the things to a continuum problem, the particle moving on a circle.
Yeah.
The particle moving
on a circle.
Line.
Let's take the circle or the line. Yeah.
Let's take a circle.
Yeah.
We suppose they put the thing on the flats through the ring.
You put a what?
Flats. Magnetic.
Okay, magnetic flux. Yes.
I mean, it's like an electric field in one dimension. If you so one particle moving, I put a flux. So I have, essentially have like instead of having p squared over 2n, I'm going to have some operator that is p minus, the equivalent of the vector potential generated by that flux squared divided by 2.
Mm-hmm.
I could like to understand the dynamics, of that problem. For example, I could put, h of t, there is some time, okay, parameter time, and have p minus a that depends the flux through the ring depends some time, square over 2.
Mm-hmm.
How can I see this if I want to have some, a mathematical representation of that process? Or every process you want to show me in the continuum is fine, but I'm putting you something that could be interesting to see, how is that diagram set?
Yeah. So if you want to explicitly integrate a generic Hamiltonian that consists of x and p terms, or functions, classical functions of x and p terms, then that is still quite complicated to write diagrammatically. And I don't know of anybody who's done it for the infinite dimensional case. That people are getting to doing it for the finite dimensional case for trotterization, for example. So you take a few terms and you want to find a nice closed form for the exponential of a few Pauli terms. And that's already kind of hard in finite dimensions. As in people are working on that, but there is nothing complete at the moment. People have various representations that may or may not be useful, but nothing that says this is a nice way of representing the exponential of a Hamiltonian, an arbitrary Hamiltonian. Though there is some recent work in the ZXW calculus that gets close to it quite. So it gives you a reasonable representation, even though it's fairly large. Now, the problem that you get with applying that particular technique to the infinite dimensional case is that that technique tries to do the full expansion, which for the infinite dimensional case will not work because you're effectively trying to take infinitely many terms potentially. So you need something more compact, and we don't really have that. What we can talk about is the fairly basic things such as how translations and momentum boosts interact. For example, for a free particle, we can talk about that. So we can show things like the Weil CCR.
That's okay, but I mean, but even in the case you're saying, I mean, even if you have a problem, we know that we can simulate it. If you go to a computer, you can write down, okay, if I have it where, and the only thing I have to do, and I discretize at that moment, I don't have it. Of course, I will have to make it in me. That's fine. That's I think. But how is that, you know, if because it's connected to some of the things you were saying here, but you know, it involves a different kind of structure. How is that we can use these ideas to understand those problems? Let's start with the boost one, with the boost and translations or whatever. I imagine you mean by boost, you mean
Adding velocity.
Or
Yeah, momentum boost, like adding the translation in momentum space.
oh, translation momentum. Oh, this
Yeah.
is translation.
Yeah.
Boost.
No, because translation is translation in, well, it depends how you, sure. It depends how one is used to saying it. I typically think when I say translation, I think typically imagine I'm translating the particle in space, in position space. And then when I translate it in momentum space, that's kind of imparting additional velocity. So it's changing its velocity. And I think some people say boost, but maybe that's a minority thing. I don't know. Doesn't matter. We understood each other. That's the only thing that matters. So that's slightly, so the translations in position and momentum space are easy because they are exactly the rotations of the X and Z spiders. So in the continuous case, let's say in the case of L2 of R, you have that the one way to write down the classical elements of these two bases. So these two, let's start with these ones. So I will not try to write down the phases because the phase group is very big in this case. It's obviously infinite dimensional, but you can label them by having some position in the real numbers, and you can label these ones. Actually, these ones are momenta, and in the dual of the real numbers, and these are positions in the real numbers. And you can say that, okay, so what is this? I'm gonna put around, sorry, square brackets around to indicate that this is a classical, just a classical point that corresponds to a very specific phase. It's not just the angles. So this one on the left is translation by P in momentum space, and this one on the right is translation by X, sorry, by X in position space. So these are easy to write because they are the exponentials of the Z and X, of the X and P observables, if you will, of the position and momentum observables. So those are straightforward. If you try to exponentiate something which is a sum of terms, it becomes more complicated, of course. It still is the case that you can take combinations of these rotations to approximate your general exponential. So it's true that every exponential is just a sequence of, that's approximated by a sequence of these rotations. Like is the case, it's the case for a qubit, it's the case for anything. So these generate approximately every rotation that you can make.
Can you write the operator?
Yeah, of course. Yep. So this one is, so let's say for, how do I want to, yeah, but I want to avoid having the same letter. So yeah, T, thank you. Let's take T. This is E to the, is exp. I'm going to put the H bar into the position operator. Sorry, the momentum operator. And this one I'm gonna go with S this time. Is exp ISX. So they're the ones that you see in Vile CCRs.
Yeah,
So
this is the value. These are the trigger operator.
yeah, they're a generalization of the clock and
And the clock is a trigger.
yes,
They're
clock is trigger. And the good thing you can, I mean, one of the interesting things that you can do, and I'm sure that it will seem entirely trivial to you, but it wasn't to us, is that if you rewrite the Vile CCRs, right? You write them like that, then you can actually pull out the, states and co-states on one side. You can pull out T here, and you can pull out S here. Again, spider fusion is just the usual stuff. On the right-hand side, you can take this and pull out similarly, but you have to be a bit careful how you do it. So you try to put T on the left and S on the right, and you will use the fact that these states form a basis or an overcomplete basis, if you will. Do something like this. And now you look at them, and there's still the factor here that you need to account, but you rewrite that factor as T. So it's just that scalar, because that is a momentum eigenstate inner product with a position eigenstate, which gives you the correct factor. And now you observe that you have 2 copies of T on the left, 2 copies of S on the right. So you put copy maps in there, so you have a single one. You rewrite the left. Oops, I'm so sorry. You write the right-hand side again as this way. So you have the same number of basis states on the left and on the right. You have the X basis state here. You have the Z basis state here. And now you take this and you remove, because they form a basis or an overcomplete basis, you can remove them and you get an equation for the linear operators associated. And the equation that you obtain is and suddenly you discover that the Vile CCRs are just a bialgebra law for infinite dimensions. They are a consequence of in fact, they are equivalent to the bialgebra law for infinite dimensions. That is what the bialgebra law is, the commutation relation for a group algebra and its dual algebra. And this is not true just for groups, it's true for compact matrix quantum groups, it's true for anything which satisfies bialgebras. There's quite a lot of bialgebras around, not just the group algebras. And so the Vile CCRs kind of generalize to those settings. You don't just have, you can do deformations, topological deformations of these groups, and you still get this kind of relationship. So yeah, again, from the point of view of someone who is interested in the very practical problem, and by practical, I don't mean in any way not interesting diagrammatically. In fact, I mean probably very complicated diagrammatically. The practical problem of taking a Hamiltonian and doing a calculation, even in approximate ways, this seems for sure very basic. But if you extend this kind of representations, and people have not really studied how to do that yet, but they are trying, you will be able at some point to get the basis, the generators for the exponentials of the Hamiltonian. So much as in the case of qubits, you have Z and X rotations that generate everything. So in the case of infinite dimensional systems, you have some of these families of operators that can be used to generate approximate versions of the, say, unitary that describes the evolution of a system of a electron in a magnetic field on a circular wire. But it's just a matter of sitting down and doing it. And I haven't had, honestly, the push to do it. I haven't had someone come and ask the right questions yet, but at some point.
I see the ways where we analyze this. you know, one of the questions is in which ways these kind of anti-methods can help some situations where we know is not straightforward. Yeah, for example, we're mentioning before case of products, the doctorized and unitary operator. Right, to doctorize that thing, it's a big, complicated enterprise.
Yeah.
Because if you want to really do a simulation, a quantum simulation, dynamic simulation, you will need lots of gates, lots of things.
Yeah.
So when you showed before, for example, the examples you were talking about the supremacy, and all this stuff is connected to the fact that there are ways of optimizing the end. Okay?
Yeah.
So, for example, are you considering this type of ideas, graphical ways of optimization of this tokenization?
Yeah.
It's an example, no, of many.
Yes, absolutely. I can give you one practical example. So there's a few things that you can do when you decide to look at retrotorized Hamiltonian. I'm going to take the. Can I take a simple example from, say, Quawa? Are you happy with that for me to start? It's not the most exciting, but it is a very practical one that people use. So you have a group. So you have a graph, one of these Ising Hamiltonians, and you construct the Quawa circuit for a problem on this graph. So you have couplings and biases on this graph, and you construct Quawa, and you look at the Quawa circuit, and the Quawa circuit looks something like this. So it starts with a plus state, and then you apply a bunch of exponentials, so phase gadgets, but you typically have to write them like this. I'm going to ignore the fact that I'm not going to label all the angles, or maybe I will. I don't know. I'll try. Let's see. Beta. Then you have one for this. Beta. And you have one for the main. So 1, 0 to 3. Sorry, 0 to 2. Something like that. And then on this side, you have one that goes like this. Okay, so this is kind of one layer, let's say, of Quawa for this graph, with angles that are proportional to whatever biases and couplings you have, plus all the single rotations that correspond to the biases at the end, plus the X rotations that correspond to the mixing Hamiltonian with their gamma term, with their gamma angles. And then you repeat this layer again and again and again and again and again. Okay, and now you stare at this and think, okay, this is the algorithm that I give for Quawa. What does it mean? Why does it work? How do I understand this algorithm? And of course, you can look at the exponentials. You can go from trotterization to sort of optimize annealing schedules. And there is the proof that Quawa works, or there's the taking that particular diagram and making it clear that the thing this circuit does is create entanglement in exactly the same shape that the problem does, with exactly the same correlators that the problem has. So doing what effectively the way that, say, D-Wave tries to explain why their machines work when they do their outreach webinars. The first step in doing so is to observe that some of these pieces are poorly drawn, or in a sense, they are not as clear as they could be. So we start with what is the basic building block. The basic building block is a little thing done, which looks, it's a little bit of circuit that looks like this, with some angle. And this is the exponential of ZZ. So was it EI theta 2 ZZ? I think it's the correct one. And now that's one way to obtain that exponential, but it's not very convenient to work with. First of all, it has too many pieces. And secondly, it doesn't show that it commutes with Z terms on the left and on the right. that it could fuse with those terms. So you rewrite it by observing that this is an example of bialgebra. It's you fuse. In fact, let me do it properly. This is the
Let me ask one question before you.
Shoot.
I mean, if you're using a problem, just for the graph, it's just a classicalizing model, or is
let's take a classicalizing model. Yes, just let's take the one that they used to sell us the utility of quantum computers.
Okay, that's okay.
Well, not to, I guess not to you, but you have very advanced users in mind, I presume, because you understand what they can do. But most people think, optimization problems, and that's it.
Okay.
That's what I mean. So classicalizing. So first thing, I fuse and obtain something that looks more like a square, and I unfuse, so it's kind of clear what's going on here. So this is just fusion, a bunch of fuse and unfuse that brings it into a slightly more convenient form. And then I observe that there's a square, so there's a bialgebra here that I can collapse, and I replace it with 1, 2, that's what I get roughly. So let me do it in a bit more friendly way, like this. That's what I get, and I reorder things a little, and I get a more convenient representation for exactly the same exponential, which is now in the form of a phase gadget. And now these phase gadgets are much easier to work with. First, they look a lot more like correlators than the original gates. But if I rewrite the entire circuit with the phase gadgets, I get something easier to work with. So let me do that. So I have all of these spiders, and now I'll have the advantage that all the spiders that touch are all in the same basis. So here, I promise I will make a short work of it. This one. This one. Okay, now that's kind of already better. Next step, I take this and I observe that pretty much everything here is green, right? Just I'll make it a bit clearer by highlighting the bits that I will fuse. So that big circuit that I had is actually mostly simultaneous. That's part of the game. That's part of the way that QAWA works. But I can then simplify it. I can fuse all of these spiders all together in a single sort of big state, which becomes similar to a cluster state, but not quite a cluster state. So it turns out that the state that I was trying to prepare with my circuit, with one layer of QAWA, the state that you are preparing is the state that the graph describes. 1, 2, 3, 4, 5, with couplings, tunable couplings corresponding to the edges of the graph. And in fact, the strengths are proportional to the couplings between the classical Ising model edges. And so I get something like this. And yeah, and if you want to do a second layer, of course, you can prolong these to the bottom until you get the initial state. So each layer effectively looks like a single piece that is performing the coupling for the simultaneous observable. So all of the Z terms actually commute. So there's a simultaneous observable, and there is a simultaneous gadget that performs one rotation, one tunable rotation on that axis. And it's the gadget described by that piece of circuitry. And you get these, you can't represent with quantum circuits because there is no way to say that there is an operation which shares part of its control on one qubit, but then part of it is separate on a different qubit. That's not something that you can describe easily with circuits because they require unitaries, but you can with tensor networks. So you get a tensor network that, first of all, easier to simulate because that has fewer pieces than the original one. It's much easier to contract that than to contract the original one. But it also shows exactly where the tunable couplings are. So you can design new algorithms this way. You change the basis a little bit and you get the quantum alternating operator ansatz. It's just the same idea, but you change the basis of the legs. And it's much easier to tune that kind of algorithm by looking at this representation and saying, okay, it's the same, but I'm changing the legs for some of my terms in the Hamiltonian than it is to look at the original one and think, how do I replace my C naughts in the right way that I get the correct couplings? You can, of course, and people have been doing it for a long time, but it's quicker this way.
Is a property of the fact that the graph is clean?
No. And it's not even a property of the fact that it's a graph. That's actually the beauty of this. I can easily write down QAWA for an arbitrary Ising, for an arbitrary non-Ising Hamiltonian, but a Hamiltonian in the Z basis. And I just have to replace these little gadgets. Yeah.
Again, such a level.
Yeah, it's identical. It has nothing to do with the fact that it's in the plane. It's just convenient because in the plane I can easily draw it.
Like
But
plane, I mean, it's a planar graph.
no,
So that isn't the plane. I mean, I cannot put anything, three-dimensional, a plane, but the graph is not plane. Take this three-dimensional model is non-plane.
no. It has the fact that there is nothing to. It just matches whatever graph you had. That's the connectivity of the couplings that you get. But it's not just, my point is it's not just graphs. So you can have couplings, right? So J, let's say J, and here you have J theta. You can have single nodes, so you can have biases. That's the standard QAWA setup for the Ising model. But of course, we know that QAWA is not it is used mostly for Ising problems, but it is not restricted to Ising problems at all. You can do any exponential of any Z diagonal Hamiltonian can be optimized with QAWA. So you might be interested in not having to, for example, simplify three Z terms, so triple terms, the ones that correspond to the ones that arise from the end gates in a computational optimization problem. And then you can have something like this, which connects three. So it's not three edges. It's a triangle that connects three different variables. Let's say I, J, and K. Variables I, J, and K with some weight, and then you get a triple term which looks exactly like the other ones. And the fun part is you can take, first of all, this kind of representation, this gadget representation makes it absolutely clear that you can fuse all of the common legs. So you can simplify your circuit even in the presence of triple terms or higher terms in your Hamiltonian, not just quadratic. It doesn't have to be a quadratic Hamiltonian. It can be a cubic or any degree. And exactly the same formula works. Moreover, you can prove that the way that you synthesize these, say that you now have a circuit that has been fused into these gadgets, and now you want to ask, can I in some way synthesize it by minimizing the number of CNOT gates that I want to perform because I have a noisy piece of hardware. And then it's interesting that if you have some of these triple or quadruple terms, you might, let's say that we have this, okay? This is I think it's a simple example. Where I have a triple term and a square term. And now if you naively synthesize this particular circuit, you are going to have to expand the triple term into a ladder of CNOTs. So this is going to be what? This, then this, then a rotation, then the inverse ladder. Actually, I gave the wrong one. And Zena gave the one that gives away the game, obviously. Let's see a testament to that. My brain is so used to doing the simplification that it automatically picked the order that would cancel out the spiders. It's like it's a habit that you get after a while. But you can do it this way. And then you discover that your circuit can be simplified because you can remove these two and you can commute the other one away, or you can expand it the wrong way and then you can't simplify your circuit anymore. So you could expand it this way. And then your circuit doesn't simplify. Because you have no way of, you don't know that you can commute things through, you don't know that you can fuse the CNOTs, but they give you the same exact result, except one of them used this freedom of this kind of representation, which is more compact, that then gives you the ability to expand it in exactly the way which optimizes the number of CNOTs that you have in your circuit. Even more, there is a technique that uses conjugation of circuits in this trotterization, in these trotterized Hamiltonians. You typically don't just have one layer, right? You have a repeating number of layers, all the same, all identical. And so you say, oh, okay, so I look at my layer, and what I do is my circuit coincides with a bunch of repetitions of this layer. And so if I can simplify one copy of this layer, then I can simplify my circuit. Let's say that there are K1 to K copies. If I have a reduction on one copy, I get a reduction over the entire circuit. So it's sort of proportional in a sense, because of this structure. And the problem that you get by looking at it in a compiled circuit is that actually the rotations are not the same. The rotations have different angles, but the structure of the layer is the same. So if you work abstractly from the diagram and you just look at the parameterized gadgets, you simplify the parameterized gadgets and then you apply to different, like the shape remains simplified, but you apply the angles to different values because different layers of QAWA, for example, have different angles. It's the same structure, but different angles.
Yeah, but the precision is exactly the same.
In a trottery, it depends. It depends how you want to. If you trotterize by taking sort of constant steps, if your annealing schedule is fixed, then it's the same, but your annealing schedule might not be fixed. Your Hamiltonian might be time dependent, in which case the trotterization of a time dependent Hamiltonian is not. Then it is, yes, typically it is taken to be the same. I'm thinking of trotterization of Hamiltonian in the time dependent case, such as the annealing simulation in the quantum annealing. Yeah, and what you get is that you can, if you can, insert a circuit at the start and a circuit at the end. That's easy to make. Then you can sort of conjugate all of these layers. And the circuits in the middle don't really appear, but it's as if they were there. And so you can look at finding a circuit which conjugates these terms and simplifies them as much as possible. And the beauty of these terms is that they are exponentials of simple Pauli strings. So if this layer consists of Pauli exponentials, then you don't even have to look at the exponentials themselves. All you have to do is look at the underlying Pauli terms. So x, z, y, like whatever Pauli string generates the rotation. And then you make two layers, they are Clifford layers. And now you can use the fact that the Clifford group turns Pauli strings into Pauli strings, and you can use any algorithm, any machine learning algorithm to optimize a small circuit of Clifford gates, which minimizes the number of CNOTs or the number of T gates, depending what you want to optimize, minimizes the cost of implementing that block. Because in trotterization, it's always exponentials of Pauli terms, so you can just work with the Cliffords directly. And that's you can do it purely diagrammatically. You can use the shape of the graph to compute the simplification. So there are, I think optimization of quantum circuits is probably, and I believe Alex, for example, would have a strong position with Alex Kissinger. I think it is the one thing that people started doing that made these techniques more mainstream in quantum computing. They are remarkably effective at simplifying circuits, more than traditional techniques that came before. It's pretty common to see benchmarks from master students' thesis that beat previous literature. Almost every year we get one. And they just improve over these, or some of these graph complementation techniques. They look at this circuit and think of it, it's a big graph state, right? Look at this, you think, oh, it's not a circuit. It's actually a graph state, secretly, a graph state plus plus. And then on a graph state, I know a lot of things. There's a lot of tricks you can do to sort of complement, remove some legs by adding other legs. And yeah, there's quite a lot of tricks that people developed. It's a pretty big literature. If you want, I can send you a sample of what people have been doing. Maybe that's interesting. But yeah, trotterization is an interesting new direction. Because people only recently, this is the ZXW calculus, they started developing graphical gadgets to talk about sums of terms. So they introduced these, they existed a long time ago, to be fair, but they were never fully integrated with the ZX calculus. But they introduced these Z spiders, sorry, W spiders. It's late. And this is it's written as sending 0 to 0, 0, and any other J in the basis to J0 plus 0J. So it effectively treats 0 as if it were a vacuum state of a sort of vacuum state of the system, and all of the other as excited states of the system. And it does what an interferometer would do by like a beam splitter, non-polarizing beam splitter with an open port. It would sort of send the particle in the two ports. This is what this map does. But graphically, it can be used if one plugs like a one. Let's write it explicitly. If one plugs the one state in, this becomes 0, 1 plus 1, 0. And now that can be used to control terms and make only one of them appear at any given time. So if you have two unitaries and you want to write H plus K as where H and K are two unitary matrices, then all you have to do is make the control versions. There's an algorithm that takes any diagram into the control version of the diagram, make the control version of that, and then in the control, you plug the output of the spider, and now you got that map there. So the map, was it like that? So this, and you can do this for any unitaries. Therefore, you can do it for any map that can be represented as sum of unitaries. There's quite a lot of matrices that can. And then you can use the rules of these extended calculus to simplify these diagrams. And so you can make sums of Pauli exponentials that form the trotterization of a Hamiltonian. You can put them all compactly by making the control version. You just add one leg, and then you plug in this spider, and then you put it in the compiler, and the compiler runs heuristics to sort of simplify things. And sometimes it's good, sometimes it's not yet good, but this is a fairly recent development, so I'd give it some time. Pleasure, absolute pleasure. I think we've been talking for a while. Any more questions or interesting things to talk about? Terrified eyes. Not at all. Good. Yeah, please. Absolutely. So shall I stop sharing and there's a call? I think we close it here. It's almost, yeah, it's 4:40.